My name is Aman Singh, and I'm a maintainer of a new and upcoming CNCF project called Drasi. So today we will look at two demos of change-driven scenarios, and we will see how Drasi can simplify the architecture for us. Now, with everyone excited about AI, I want to open today's discussion with chat applications. So how do we build a chat application today? Well, we simply wrap the LLM model in our application code, and that allows us to ask it questions like, what is the largest country? And since the model has been trained on large amount of internet data, it is able to give us a factual answer. But what happens when we want to ask it questions about our own data? Say we wanted to build a chat application for an online electronics store, where the product's microservice was maintaining its information in a Postgres database. And the review service writes to a separate MySQL database. So how would the model respond to a question about the laptops in the store? Now, the base LLM here has a problem. It has no idea about the products in our store, since this private data was not part of its training. So out of the box, the best it can do is give us a generic, unhelpful response like this, admitting that it cannot access our internal databases. So how do we bridge this gap? A common pattern in use today is retrieval augmented generation, or RAG, where we first join the data from our sources and generate text documents from that, and then feed those documents into an embedding generator, which uses another AI model to convert the text's meaning into numerical vectors. And finally, those vectors are loaded into a vector database like Quadrant, and that serves as a knowledge base for the chat application. Now, when the user asks the question, the app would first query the vector store to find the most relevant documents, which are then sent along with the user's question to the model. And that is what allows the model to give an accurate data-driven answer containing information from both the microservices. But this brings us to the real challenge. What happens the moment the product price or description gets updated in our Postgres database? Suddenly, the answer from the chat application is wrong. And it's the same story when new reviews get added to the MySQL database. Now, our smart assistant is confidently giving customers bad information, which is arguably worse than giving no information at all. What we need here is a real-time RAG system, one that automatically updates the vector store when the data in our databases changes. So how do we make this system real-time? Well, one option is polling. We could set up a simple batch job that reads all the data from Postgres and MySQL, generate text documents using a template, use the embedding model to generate vectors, and then completely overwrite the vector database. Now, this is simple, and we are guaranteed that the results will be always consistent, but the drawbacks are not trivial. Our results will be stale by the length of the polling interval, and it is quite expensive to compute embeddings for all of the data, most of which probably has not changed. So how can we make this a bit better? Well, one option could be to poll only for the data changes, right? So we still use the batch job, but this time we track the state of our last run and we find the delta of what's new and what has changed. So what about the data that has updated, right? So, and then we call the embedding model only for those changes in the data. So we track the state and compute updates and generate embeddings only for the updates. Now this is better as it saves some of the embedding costs, but now we have traded infrastructure costs for code complexity. And we are still stuck with the fundamental trade-off of polling. If we poll too frequently, we are hammering our source databases, and if we poll too slowly, the chat application will be serving stale answers. So what could we do instead? Well, the real-time experts in the room might just tell us to use event streaming, where we subscribe to the database's change logs using tools like Debezium, publish those changes to a message broker like Kafka, and then we can write a stateful stream processing job using a framework like Flink or Kafka Streams that will join these two streams together. And that can give us a new stream of correlated updates. But we are not done yet. We still need to write more code to process these updates, generate the embeddings, and write that to the vector store. This architecture, however, is powerful. It is near real-time and has a low impact on the source databases. But the operational complexity is massive. We are now responsible for deploying and managing CDC connectors, Kafka cluster, Flink cluster, and we are still not done. We must write and maintain two separate pieces of custom code, like the stateful stream processing job here, and the whole embedding pipeline. So now we have polling, which is simple but slow, and we have streaming, which is fast but quite complex. So what if I told you there's a better way? What if you could get the real-time benefits of the streaming solution without all that complexity? And what if you could replace that entire pipeline with a single component? Well, with Drasi, this is how simple the architecture becomes. No more writing custom code or maintaining multiple systems. All we need is a set of config files, and Drasi handles the rest. So let's see how that would work. So we start by defining our sources. So these YAML files tell Drasi how to connect to our data sources. Now, notice here that we don't need to copy our data into Drasi or some centralized data lake. Drasi meets your data where it lives today. For example, this is what the YAML would look like for our Postgres database. So it has some basic connection details like the database name, the table name, pretty standard stuff. And with that simple YAML file deployed to Drasi, it is now connected to our Postgres database. We need another one for MySQL, which is pretty similar. And when we apply that, Drasi can handle the connection and the underlying change detection for both the data sources. Now, once connected, Drasi allows us to query data coming from all these various multiple disparate sources as though it was all part of a single virtual graph. And that allows us to write continuous graph queries like shown here. Now, notice that the query here does not care about streams, windows, joins, watermarks, none of that. It is simply declaring the final joined result set that we want. For instance, here we want to match the products to the reviews, and we want to calculate some aggregate review statistics. So now normal database queries give us a result set, which is a snapshot in time, right? So when you run a query, you get the results based on how the data looked at that particular time instant. Drasi queries are a bit different, so they act as if they are running continuously. Basically, these queries maintain a perpetually accurate result set. So Drasi is always watching your data sources for incremental changes, and as those changes happen, Drasi will always keep your query results up to date in near real time. Now, the queries are maintaining this live result set, right? So the question is, what can we do with this live result set? Well, the final piece of config tells Drasi about the actions that you want to take with this live result set. And we can also tell Drasi what to do when the result sets change. So this is the simple YAML file for our RAG scenario. So here we are telling Drasi to use the embedding model from OpenAI, store the embeddings in a local vector store, all of that. Now with that reaction in place, Drasi can handle the rest. The document generation using templates, embedding generation using models, updates to the vector store, everything end to end. Now let's see that in action. So here I have a demo where I have set up a MySQL database, which has the reviews information, and I have a Postgres database, which has the products information. I also have a quadrant vector store. Let's jump inside the Postgres database, where we have the products table containing some electronics items like laptops, phones, tablets, etc. And in the MySQL database, we have a reviews table, which has reviews for the same products that we saw earlier. Now for the quadrant vector store, we could use the curl command to investigate the contents of the collection. So I've written here a simple script that will fetch the product knowledge collection from the vector store. And if found, it will report back the total number of points found in the vector store and the most recently updated ones in the collection. Now, all of this is wrapped inside a watch command, so that'll give us the results every 2 seconds. So let's go ahead and use this script. So right now, the product knowledge collection does not exist, so let's use Drasi to build that. So we start by going to the Drasi website and use this simple command to download the CLI for Drasi. And once the Drasi CLI is installed, all we need to do is run a simple command called Drasi init. Now, this will install Drasi onto our existing Kubernetes cluster in an isolated namespace. And with that, Drasi is up and running, and we can start writing our sources. And here's a simple YAML file for our Postgres database. It has some basic connection details, the table name, just like I showed earlier. Similarly, we have the second YAML file telling Drasi about the MySQL source and the reviews table inside that. Now we can use the Drasi CLI similar to kubectl, just use the Drasi apply command to apply the sources to Drasi. And with that, these sources are now available for us to use. So we can start writing our continuous graph query. So we start by declaring the two sources that we want to use, which is the same one that we saw earlier. So the Postgres is providing us with product entities. And remember now, Postgres is relational database, but Drasi query is going to be graph-based, right? So each row in the products table will be represented as a graph node for the purposes of our query. Now, similarly, MySQL is another relational source that will create graph nodes for every review in the reviews table. And in the join section, we can tell Drasi how to connect data coming in from all these different sources, right? So here we are telling Drasi that we want to create a has-review relationship between the products and their respective reviews. And we can tell Drasi explicitly that we want to connect product node with ID B and the review nodes that have the same value B in their product ID field. And with that graph model in place, we can now write the simple graph query that looks like this. Now, we have a match phrase here that captures all the products and their connected reviews together. And we can then project out some of the fields for the product nodes and compute some of the aggregates over reviews. Here, we are computing the average rating and the number of reviews. So let's go ahead and deploy this query using the CLI. So when this query is first deployed, it goes into a bootstrapping phase when the indexes are being built. So it gets online in a couple of seconds. And once it's online, we can use the Drasi watch command to see the live result set that it maintains. Now, what do we do with this live result set? Well, we want to materialize its embeddings in the vector store, for which I'm going to use the final piece of config, this reaction YAML. Now, this has also the text template that will basically have values embedded in it from the Drasi result set and which will be sent to the embedding model. And here, I define that I want to use the Azure OpenAI embedding model called text embedding 3 large. And I'm also providing the API key and the endpoint for my model in Azure as Kubernetes secrets. Finally, I'm also giving details about the local quadrant vector store that I'll be using. So let's go ahead and deploy this reaction with the CLI. And on the left side of the screen, we see that the collection gets built in real time and 9 entries are added to it as the reaction comes online. So that's basically being done by the Drasi reaction. Now, with that vector store populated, we can use this chat application that I built here. And this application is connected to the local quadrant vector store. So that allows us to ask questions like, what laptop options are there in the store? So here we see that the app first found the 3 relevant documents from the vector store. And that allowed the model to basically reply back with 2 laptops and their specifications and the aggregate review statistics. Now, if we look back in our Postgres database, we can see that it has the very same 2 laptops. And in the reviews table, we can confirm that the first laptop indeed had 2 reviews and the second one had only 1. So how about some updates? So let's try some updates. Now, on the left side of the screen, we are watching the vector store collection, which has 9 data points. Now, if I connect to the databases and add a new laptop in the Postgres database and add a couple of reviews for that, so we should be able to see the collection get updated immediately. And in a couple of seconds, we see that the new data point got created in the vector store for the new laptop. Now, if we switch back to the chat application and ask the same question about laptops, this time, we see that the 3rd laptop appears in the result set. So right now it has a perfect 5-star rating across 2 reviews, which we just inserted. So let's add a couple of mixed reviews for that. If we head back to the MySQL database and add a couple more reviews, a 3-star one and a 4-star one, and try the same question one final time, we again get back those 3 laptops, but this time the review rating for the laptop has been updated. So we saw that with just a few config files, Drasi has helped us build a synchronized vector store. And this is a perfect example of a very common and powerful pattern, a derived view. Now, a derived view here is a materialized view of our data that has been derived from one or more sources and has been transformed for a specific purpose. In this case, for fast retrieval by an AI application. And this need for derived views is everywhere in modern architectures. Now, we often have data scattered across multiple systems, and we frequently need to create a unified view of that data to power new scenarios. Now, the vector store for RAG is just one example, but Drasi can help you with other derived views as well. For example, what if we wanted to build a real-time web-based dashboard that shows product analytics? For that, we would need to pull data from multiple services, right? So we need data from product microservice, inventory microservice, reviews microservice, etc. And we need to provide that information in real time, combined together through maybe a WebSocket server for our front end. Now, the web-based dashboard in this case could also be viewed as a derived view on our data that is spread across multiple services. And Drasi can help us keep that in sync. One of the pre-built reactions that we have in Drasi today is a WebSocket server. So with just a couple of few YAML files, we can have a custom WebSocket endpoint ready to power your front end. Now, within microservices, another common pattern is called CQRS, or Command Query Responsibility Segregation. Again, here, the read models are also just another form of derived views that are optimized for fast queries. And Drasi can help us with that. Now, this brings me to the bigger picture. Maintaining derived views is just one critical pattern within a broader category of software design called change-driven architectures. Now, we define change-driven architectures as those where a system must perform a timely action in response to critical data changes. And that is the core problem that we have set out to solve with Drasi, providing a new, simpler way of building these kind of systems, a more cloud-native way of building these kind of systems, rather. Now, another manifestation of a change-driven architecture is when we need to trigger real-time actions in response to changes in state, which may be distributed across multiple systems, right? So when data changes, that could be a trigger to start a new action or a workflow. Now, think about a building management scenario where you may have sensors deployed in different rooms, and if temperature of one or more rooms increases, we want to activate the cooling or the HVAC system. Another example could be automatically executing a reorder workflow if your inventory levels drop in your inventory service. What about a scenario that is very relevant for many of us in the cloud-native space? Alerting teams when a container image with known issues is found to be running inside your Kubernetes cluster. So let's dive deeper into that one. The scenario is classic. We have a development team and a separate security team. Now, the development team is deploying their services and pods to their Kubernetes cluster. And meanwhile, the security team maintains a list of known risky or non-compliant image tags that they don't want to see on the Kubernetes cluster, right? So this is being maintained in, let's say, a completely separate Postgres database. Now, the change-driven problem here is this. The moment the security team identifies an image to be risky, we need to find all the pods or services that are running with that particular image in the Kubernetes cluster and trigger an alert for the respective team. Similarly, the moment a new pod or service starts running with an image that matches an entry in that security team list, we again need to trigger an alert for that particular team as well. So without Drasi, you might be forced right back into the world of writing custom polling logic that deals with the Kubernetes API, maybe even a Kubernetes operator, a controller, all of that. Or maybe you might think about writing a custom stream job that correlates these two data sources, use Debezium, Flink, Kafka, and all that. But all of that is just too complicated. And we now know that there's a simpler way for designing change-driven solutions. So how does the architecture for this scenario look like with Drasi? Well, it's the same simple architecture that we saw earlier. We have YAML files telling Drasi about the Kubernetes cluster that we want to watch, and also the security database. And we declare the condition that we want to monitor with a simple graph query. And then we can configure the reaction to send alerts wherever we want. This could be Slack, Prometheus, or PagerDuty, whatever you want. Now let's see that in action as well. So we have a Postgres database running here, which has a list of risky images, which is maintained by the security team, including the image tag, the reason, and some mitigation steps. Now I also have a K3D cluster running, which will be the Kubernetes cluster owned by the development team. Now, this time instead of the CLI, I'll use the Drasi VS Code extension. So the VS Code extension shows us the sources, queries, and reactions that are already deployed. And it also detects the YAML files that are in my workspace already. So let's start by looking at the sources first. So here, just like we've seen before, the Postgres YAML file telling Drasi about the Postgres database and some basic connection details. The second one is a bit more interesting, which is telling Drasi about the Kubernetes cluster. So here, what I've done is I've captured the kube context of the K3D cluster and stored it inside a Kubernetes secret, so that's what I'm using here. Now with that, Drasi can watch our K3D cluster, so let's deploy these two sources directly from within the editor. So I can do that because I'm using the Drasi VS Code extension. Now we see on the left side the sources are coming up, and once those sources are deployed, we can start writing our query YAML. Now we start in this by declaring our sources, the first one being Kubernetes, which is creating pod for every cluster, we're just creating a graph node for every pod in the cluster, and we also extract out the containers from those pods, creating a node per container, each of which has an image tag. And then we also have the Postgres source telling about the graph, creating the graph nodes for the images that are deemed to be risky. And in the join section, we tell Drasi how to connect these two. So we have a has-image relationship that will connect the container nodes with the risky image nodes only when their image tag value matches. Now with that in place, we can write our graph query like this. So we have a match phrase here that selects all the pods and their respective containers only when the has-image relationship exists. So remember, this relationship will only exist when the image tag of the container and the risky image that is being fetched from the database matches. Now, if we deploy this query and watch the live result set, let's see what happens. So we don't see any pods right now. So that's because I've not deployed anything on the K3D cluster. So I'm going to deploy two pods here. The myapp1, which is using an image called myapp version 0.1. And if you see in our Postgres database, this has a known security risk as identified here. And I'll also be deploying another pod called myapp2, which uses the image myapp version 0.2, which does not have any risks so far. And as soon as I use the kubectl command, we will see that the Drasi query instantly detects that myapp1 has a security risk. Now, what can we do with this kind of live result set, right? So as I said, we can send alerts to Prometheus Alert Manager, PagerDuty, but here I'm going to use an HTTP reaction. Now, this is very versatile. It allows Drasi to invoke any arbitrary webhook. For instance, here, I'm going to invoke a Slack URL, Slack webhook here, which will help us send messages to a Slack workspace. Now we tell Drasi here that when new results for this query are added, we want to send a message saying risky container detected to the Slack channel with these particular details. And when the query results get removed, we want another message saying risky container resolved. And here is the simple Slack channel that I've created. And as we can see, I've enabled the webhook for this particular channel. So as soon as I deploy the reaction, we should be able to see a message for the myapp1 pod in this channel. And there we go. So we see that the message has been posted in the Slack channel with all the relevant details. Now, let's say the security team identifies an issue with the image version 0.2 as well. Say they found a critical bug with that image as well, and they updated their database like this. Now, they don't need to talk to the development teams or find the pods. They just need to update their database, and the Drasi query results sets update, and we also see the respective message get posted to the Slack channel automatically. So that is pretty real time. Now, let's say the development team decides to follow the mitigation steps listed here. So what can they do? They can use the kubectl set image command like this to update their pod, to update the image version that they're using to, let's say, 0.3. And as soon as they do that, we see that the Drasi query detects that in real time, and the reaction will post a relevant message to the Slack channel. So we have seen two scenarios here where we wanted to react to changes happening in our data, and Drasi was able to simplify the architecture significantly. We just use simple YAML to configure our sources and reactions, and then we declare the business logic in intuitive graph queries. No need to worry about individual changes, how do we track those, watermarks, windows, all that, or even writing custom code, right? We just use reusable components called sources and reactions and write our declarative query. And we have pre-built sources today for a wide variety of systems. And we also have custom SDKs that allow you to build your own sources. Now, with these sources, Drasi allows you to power new scenarios that rely on joint data coming in from multiple systems without forcing you into a big data migration project first. And reactions are also ready-made code components that you can use to act in a wide variety of systems. Now, these allow you to build scenarios without the headache of maintaining custom code. Now, because of vibe coding, you can always write custom code, but maintaining code is another problem, right? And we also have SDKs to build your own reactions too and share with the community. Now, Drasi is open source, so I would like to invite you all to join us in the endeavor of simplifying change-driven architectures. And with that, I would like to thank you all for joining us. Please check out these links, and you can also find us at the Project Pavilion in the exhibit hall tomorrow. And please use this QR code to provide us feedback on the session. And yeah, I can take a couple of questions now.
Hi, thanks for the talk. It was really, really cool. I was curious about scalability. Have you run some load testing on, for instance, a database that gets, or I guess the question is more on the, I didn't quite see if there was like a configuration on the frequency on the queries that you're running.
Right. So the query, the name is query, and it is written as a query, but we don't repeatedly run that, right? So it's acting as though it's running continuously, but effectively what we are doing is we are maintaining all of this data in our indexes intelligently. So what we are doing is, think of, if you're thinking about relational databases, for example, like Postgres, right? So think of the replication log of Postgres or the write-ahead log of MySQL. So we are just following those logs, and whatever delta we get from those databases, we just apply those to our indexes, updating those the result set, and that's what is used to trigger the reactions.
I see. So
yeah. Sorry, go ahead.
Sorry. And so speaking to that, for a database that gets updated, thousands of times per second, for instance, like what would that look like?
Yeah, so we have tested it already, at least up to around 1,000 changes per second in different databases. So yeah, that's the scale that we have tested so far, and we are actively developing new techniques to increase the performance further. But yeah, so there's no like tweak in the YAML itself that you need to control. You can go with whatever scale you have, and then if you look back at this architecture, so we have three components, right? The sources, the queries, and the reactions, right? So the sources are the scale units for your sources, right? So you may have, let's say, a very heavy source that changes very frequently, right? So you have, let's say, a Postgres source that is changing very frequently, and maybe the MySQL one is changing less frequently. So those are the scale units for your data sources. And those gets deployed as individual components like pods inside your Kubernetes cluster. So you can control the scale there.
Oh, I see. So the components inside Drasi, the controllers, they auto-scale?
Right.
Or you can configure scaling manually?
Yeah, so the scale story, like the auto scaling story is still not complete. So we are actively working on that. But yeah, in terms of scale units, so the sources are independent scale units, and the query container is another independent scale unit. So let's say you have a query where you need more and more resources because it's detecting very important changes for you, which are happening very frequently, right? And maybe there's another query which is not so important, and maybe data changes once in 6 months. So that can have less resources. So we have tried to isolate these three in like separate scale units. So you have reactions, sources, and queries. So that's what the scale units are today. We don't have like controls in the YAML today, but yeah, that's a good idea. Maybe we should add a couple of controls there.
For sure, yeah.
Yeah.
One last question regarding, I guess it's more on the RAG-based example that you have, but I can imagine for our company, a lot of concern being on the permission model on the data. I was curious if you've implemented that in Drasi, or you leave it up to that separate RAG component.
Right. So this is a very interesting point, right? Because even with agentic RAG getting more and more popular, right? So what if the agent can write a SQL query directly? So would you even need the vector database in the first place is one of the questions that people ask, right? And that is kind of tied to the question that you asked, right? So now, let's say if we gave agents directly access to all of our production data, they might leak some sensitive information which we don't want people to have access to. So which is why you may have like separate tables, right? So where you only have the relevant data, and then whatever data that you want to give access to the agent, you can provide that particular role to Drasi to access that particular table. So you can use like managed identities in Azure or AWS, etc. So you can use the IAM capabilities of those cloud providers to manage that. And you can also use like on-premise databases and their own security model for that.
Yeah, that makes sense. Thank you.
Yeah.
Hello, I just had one question. First of all, great demo, and not in just in terms of like technology that you have built, but in terms of logistics, it was super easy to follow. Great job in that.
Yeah, thank you.
One small question, like, do you store any state between when the queries are done and the reaction consumes them?
Right. So I think your concern is more about like, will we miss any changes, right? So let's say the query has detected some changes and then we deploy the reaction later. Will we miss out on some of those changes in between, right?
My question is more like, is the query portion of Drasi stateful?
It is, yes. So
Okay.
basically, the query result sets are maintained in our graph indexes. Now, these indexes can be persisted in different kinds of stores, and we provide a pluggable model for that. So you can use either the in-memory model for testing or development,
Good.
but for production scenarios, you could use RocksDB or Redis or Garnet. So those kind of stores are available for use.
Got it. Yeah, makes sense. And is there any limitations on like what sources, like do sources need to support some kind of change driven on their end as well? Like, is there any limitation on that?
So no limitation per se on the Drasi side. What I would say is that if your source already has a change feed, so that is a very natural fit for us, right? So for example, let's say Azure Cosmos DB or multiple different databases have change feed ready for us to use, right? So that is a very natural fit. But we can also use other systems, like, for example, we saw in the second demo, we were watching a Kubernetes cluster. Now, Kubernetes cluster doesn't necessarily have a change feed, but it has a watch API that we can use, and it also has those resource version timestamps that help us track what is the change happening between different states, different versions in the resources that are deployed on top of the cluster, right? So if that kind of information is available through some kind of API, so we can, of course, use that to build the Drasi source.
Got it. Makes sense. Thanks a lot.
Yeah, thank
Super
you.
cool stuff.